So today we will talk about quantum superposition. Sorry, not superposition, tunneling. Okay. So talking about quantum tunneling, we will be talking about let's suppose we have a potential well, okay, and the property of this well is between this 0 and L, okay, and between this 0 and L, the wave function, or not wave function, potential energy. Our main thing will be potential energy here. Potential energy and um, energy. These two will be our main topics. Okay. So potential energy is zero in the outside part of the well, but talking about the middle one, potential energy in the middle is actually um, potential energy in the middle is actually, it should be more than the energy. Okay. So what I'm trying to say is, for quantum tunneling to happen, okay, potential energy must be more than the energy in such a way that the wave function, wait, let me use a different color, the wave function will reach a non-zero value. Okay. Now, what do I mean by non-zero value? Okay, so um, I suppose we have a particle. Okay, in classical mechanics or classical physics. Okay, classical physics. So what I just wrote here is, when in classical mechanics, if let's suppose we have an object here. Okay, when the what was it? When the property of this object, let's suppose the measurement which will be done is, what will it be, as let's suppose distance, that distance will have a definite value, right? But what will happen in quantum mechanics is, when we have a particle and it moves in a certain range, the the value we will get will not be only one. The value attained for for the particle to be at a point. I think I'm talking about superposition as well, but since they all are mixed up, they will have some common things. The value attained for the superposition to the particle to be at a point will be probabilistic. Okay, this probabilistic. Okay, now what do I mean by this is the wave function. We will have a wave function. Okay, a wave function which will define where particle will be. Okay, so it's the same for the tunneling as well. Now what I want to talk about here is non-zero value is, now we will take it to as, if this is a wall, I suppose this is a wall, and a particle rushes towards this wall. On the point when it will contact it, on the point of contact, point of sorry point of contact, this is what point of POC is, point of contact. Okay, now what I mean by point of contact is the moment it will touch the wall, there will be a wave function at this point which will value have any value but not zero. Okay, any value fit or wave function okay. So now what do we mean by it will not have zero? Means it will have chance. Now here chance is the word chance or the probability is very important, because in quantum mechanics nothing is nothing is fixed, nothing has the exact or definite values, everything is probabilistic. It will have probability of phasing. Okay, now that probability can only happen when happen when v is more than e, and when this wall over here, when the wall sorry when the wall and the particle contact, the equation we will get to calculate that wave function is a e minus k of x, where k, it's not k actually, it's called kappa. Okay, this kappa over here is nothing but square root of 2m v minus e over h, this at Planck's constant square. So this is kappas, and to derive kappa, actually this kappa came from the Schrödinger equation. Okay, equation that I this equation over here, it was not like this. It's not like this. We take it as fully E with the wave function of x depend on if you want to take time dependent or not, and then minus h bar square 2m dx square, sorry, not dx, d plus v of x, and here we have a certain value of v, so we will not put it as 0, because if, let's suppose, if it was 0, this whole thing would be 0. But so we can write over here, down here, that equation when potential, sorry, is anything but 0. Okay, so now what could be our main hint, that how can we convert this equation into this kappa? So when we rearrange the equation, the Schrödinger equation, okay, what we see is this, which is that as 2m so when we rearrange this, 2me, or sorry, not 2me, v minus e over h bar square of yeah, and what this whole thing is taken as nothing but is kappa. It's actually kappa squared. So on taking its square root, we arrive to 2m. Sorry. This is what we arrive to. Okay. So our main concern should be this form of the equation. We can ignore right now the other form, so we will just look at this one. Now this means this equation fits in this. This is the equation. This is where they should fit. Here it will not be possible. Here it won't be possible, as v are 0 there. V equals 0. V equals 0. Then when we talk about the, yeah, so this is the quantum tunneling. Now while we were talking here about the position of finding the particle, we could talk about another topic together with it, because quantum mechanics can be combined. There are multiple topics interacting with each other. So we could talk about Copenhagen interpretation. Was it Copenhagen interpretation? Something like that. Interpretation. Interpretation. What it says is, let's suppose we have a particle, and we have a particle. It moves in the in x direction. Okay. Now when it's when moving, what we will see is we will have particle. Now here, um something to be observed here is, as I cannot draw the other way, take take it to as, or assume, the more smaller the particle is, the less visible it is. For now, as of I cannot draw the slide, so assume that the smaller the particle, the less visibility you will have of the particle. Okay, so this is what Copenhagen interpretation actually is. If we have a graph, if you have a graph of, like, let's suppose here it's 1, 2, 0, -1, -2, on, sorry, on not observing. Okay, shit, sorry, I'm so sorry. Observing, what we will observe is, what we will actually observe, oh no, sorry, what actually we will be is that this image over here will be in the point where, so what we will observe is, if I take this image and copy it, after copying, wait, sorry, what, duplicate, this is what the particles should look like. Not observing should be our key point here. Okay, this is what it should look like. Okay, now the moment observation is made, right now we can say this is a quantum system. Okay, the moment observation is made, what will happen is, this particle will, let's suppose, appear somewhere over here, or like, let's suppose directly at one to make it easy. Now what will happen here is, we have now transferred to classical system. Okay, in which we have a definite value for the position of the particle, definite value. So this is what Copenhagen interpretation is, that on the not observing the particle, it has all the states, which is true, which is the main thing, that it will have many states, it will have all the states all. But here what will happen is that from states all, we take its, oh wait, this, what actually will happen is, we'll get a certain value of a certain position. Let's suppose this state, this is this state. Okay, so this is how we will get the probability of it being in this state. So this is what Copenhagen interpretation is, that interpretation is that on not observing particle is in a mode of a wave function. Okay, if we notice properly, this is what the wave function makes, right? Sorry. So means, the more we are, wait, let me change the color to white. The more we are on the end parts, the less the probability. The more we are on the top parts, the more the probability. This, wait, sorry. Red line however means high, and white will mean low. So what we will talk about is, Yeah. So this is the wave function of the state in multiple states. Sorry, particle in multiple states. And now look at the wave function. It has narrowed down. The width has decreased to the point where the probability of finding this particle at this point is high. So now we have a classical system. This was a quantum system. This one should be different color. Okay. This is Copenhagen interpretation that not observation is quantum system, but on interpretation we turn it into a classical system that we have a definite value for the um, particle to be found at certain point, and we have different all the values or probabilistic values of finding it at all the points. States are in a superposition state is in a it's in a superposition state. Then we have other one many same. We are still describing the how we interpret quantum mechanics. Many worlds interpretation. Okay. Now, what are we actually checking here? Many worlds interpretation says same. We will just bring the particles back. Duplicate. These are our particles. Okay, I made it double. Now, what are we talking about here is when it's in a quantum mechanics or quantum system, what happens is, again, I'm repeating the same thing for a while. States, superposition state. Now what will happen? Many words interpretation says we can have many scenarios depending on how, or okay, we'll go on with how it is. Let's suppose many words interpretation means if we have many words like world 1, world 2, world 3, and world 4. Now, in one world, particle could be found here. Second world, it could be found here. Third world, it could be found here. And the last world, it could be found here. Now, what's happening is in all the scenarios, the observation, this is how scientists took it as observation is and is direct is sorry correlated or entangled to uh, observed. Okay, meaning that this could happen in this world. Some observation is made and then we got something. Observation, let's suppose P1, observation of P1, sorry P2 and P1. like this position could be there. In the second one, this is what the position we got. In the third one, maybe we got the same position. Into this one, we got the same position again. So what I'm actually trying to say is, it could be a little rough, is that what if there's a connection between the observer observer and the information observed. Okay, so, and this is how they take scientists take it as, they take it as many worlds interpretation take it as own measurement own measurement own measurement, both the information and the observer, or whatever happening at that point, are in quantum system. So here we were taking we were talking about quantum system in such a way that the observer is still in a observer is in classical system. Here both are in quantum system. Okay, so what we could have what we could say is, on measurement we could have all the scenarios, or before measurement quantum system of person and particle is in all states. Word 1, 2, 3, 4, and so on. But the moment you make moment measurement is made, all these move to one world. Okay, so in Copenhagen interpretation we were mostly looking at the wave function, but here we are mostly focusing at Copenhagen. Main focus is wave function. Many world interpretation, main focus. Quantum system of both uh, particle and the observer. So, what are we talking about here? Is this was just a difference? Sorry, we're not talking about it, which is just a difference. So we covered. By the way, man, these are all the ways interpretations are actually a way to try to explain how the weird behaviors what weird behaviors are, what quantum mechanics is all about, because you don't get anything more of definite value, but you get more of probabilistic value. Interpretations are actually a way to try to explain how the weird behaviors of quantum mechanics are. And this is what quantum mechanics is rich about. One of the mostly right proved and successful theory is quantum mechanics. Yeah, that's it. Thank you.